All right, so now we are finally ready to introduce the most general method called support vector machine. So sometimes it is possible to separate the classes, but not by a line. So look at this example. Now we are going to take all the three classes of iris flowers together, right? And we are going to try to separate the one that is in the middle, versicolor, which sits here. Now, I have just encircled it, and this circle is a reasonable decision boundary, right? So if in future we classify new data, so everything that is in this circle as versicolor and everything that is not in this circle as not versicolor, then it is going to be a reasonably good classifier, right? So now I'm going to classify versicolor versus the other two, right? So -1 means either setosa or virginica. So it's -1 here and -1 here. And of course, you know, if you just try to separate them by a straight line, it doesn't make sense. It's impossible. So what we are going to do instead, so the idea here is that we're going to just introduce the third variable, right? So the center of our data is somewhere here. Right? So this is the point 4 and 1.25. So if as the third variable, I'm going to say introduce the distance from our observation, from our training data point to this special point 4, 1.25, then basically I am going to be able to separate the classes by making leverage of this third variable. So here is how it works. Now, so there is no linear boundary, right? But if I map my data into the 3D space by letting z to be equal to this distance to this special point, then this is what the data looks like in the 3D space. And you see that in the 3D space, it is possible to separate them by a plane, or reasonably well. So I mean, there is going to be a bit of misclassification here, but overall it's going to be all right, right? So now it's going to work. So our hyperplane is probably going to be z equals something. So if z is bigger than this number, then it is either one of the other two classes, and if z is smaller than a certain number, then it is going to be our versicolor, right? And geometrically, a plane in this 3D space, well, a plane z equals some constant in that 3D space is a circle around centered at the given point in the original two-dimensional space. Okay, so now let us see how these support vector classifiers perform. So how these linear support vector classifiers perform. So linear support vector classifier is the same as the soft margin classifier. Right, so on the raw data in the two-dimensional space, basically we cannot distinguish the positive class at all. So everything is predicted to be -1. But with this extra variable z that I just cooked myself, by the way. So I didn't really fit anything, so I just looked at the data and came up with this idea to introduce this third variable. The accuracy is now very impressive, right? So it's 97%. Right, so what happened here, again, so let us review, is that we came up with this function that transforms our data that originally lives in the 2D space to the three-dimensional data. All right, so and now instead of looking at the original data, we are going to look at the image under this function in the 3D space. And the original support vector classifier with two variables, so which means that we are finding W1 and W2. So we are going to train another classifier with 3 variables, right? So enlarging the feature space, basically we introduced this new feature, Z, and we are going to get this new optimization problem, which is the same thing as the original one, only, so the only thing is that we included this extra term for W and this extra term into the constraint. Okay, so that was all about the main idea behind support vector machine. So this is what is going on here and why we sometimes need a nonlinear decision boundary.